26 light-years from Earth, a cosmic paradox has emerged. The James Webb Space Telescope, JWST, has detected water vapor on GJ486b, a rocky exoplanet where surface temperatures could melt metal. This super-Earth orbits its star so closely that a year lasts only 36 hours, and temperatures soar to 800 degree F, 427 degree C. Conventional wisdom suggests no atmosphere should survive such harsh conditions. Yet, water's unmistakable signature appeared in the infrared light filtering through this alien world. But here's the twist that has astronomers locked in debate. The water might not be on the planet at all. It could be hiding in cooler spots on the star itself. A cosmic mirage that would shatter what appeared to be the first atmosphere ever found on a rocky planet beyond our solar system. If you're captivated by this journey through the cosmos, hit that like button and subscribe to Stellify Science to join us as we explore the universe's greatest mysteries. We're about to dive into one of the most controversial discoveries in exoplanet science. Prepare yourselves. We begin. The signal first appeared on screens at the Space Telescope Science Institute, like a whisper from another world. Scientists, having pointed humanity's most powerful eye at a rocky planet, 26 light-years away, expected to find nothing. Instead, the data streaming back from the James Webb Space Telescope revealed water vapor. This discovery sent shockwaves through the astronomical community. Water vapor simply shouldn't exist where they found it. This wasn't a gas giant like Jupiter, where finding water is common. This was GJ486b, a rocky super-Earth. If the signal is real, it would mark the first time anyone has ever detected an atmosphere on a rocky planet outside our solar system. The telescope observed GJ486b as it crossed in front of its star twice, each transit lasting about an hour. During those precious minutes, starlight filtered through what would be the planet's upper atmosphere. This light carried chemical fingerprints, and buried within them was the unmistakable mark of water molecules absorbing specific infrared wavelengths. 3 separate teams analyzed the data using different methods, all reaching the same conclusion: water vapor. However, the story takes a strange turn here. The water might not be part of the planet at all. Red dwarf stars, like the one GJ486b orbits, are covered in dark, cooler star spots, similar to sunspots on our sun. These star spots can be cool enough for water vapor to exist within the star's own atmosphere, rather than the planet's. Researchers ran computer models comparing both scenarios: a planet with a water-rich atmosphere and star spots with water vapor. The resulting spectral signatures were nearly identical. Sarah Moran from the University of Arizona, who led the study, put it bluntly: "We see a signal, and it's almost certainly due to water, but we can't tell yet if that water is part of the planet's atmosphere or if we're just seeing a water signature coming from the star." The uncertainty is maddening. For decades, scientists have hunted for atmospheres on rocky exoplanets, finding them on gas giants but never on a world resembling Earth in composition. Even if it resembles hell in temperature, the stakes couldn't be higher. If GJ486b has an atmosphere, it would prove that rocky worlds can hold onto their air even in the harshest environments imaginable. If a planet this close to its star, this scorched and bombarded by radiation, can maintain an atmosphere, then what about the billions of cooler, calmer worlds orbiting within habitable zones across the galaxy? But first, we need to understand what kind of world could even survive in such a place. Imagine Earth, squeezed to weigh 3 times as much, while only growing 30% larger. That's GJ486b. The gravity on this world would be crushing. your weight would triple. This is a super-Earth, a rocky planet more massive than our home, but smaller than the ice giants like Neptune and Uranus. Scientists confirmed its existence in 2021, detecting the telltale dimming of its star as the planet passed in front. The planet resides in the constellation Virgo, but GJ486b is anything but gentle. Its surface temperature hovers around 800 degrees F, 427 degrees C. Hot enough to melt lead and zinc, hot enough to turn solid rock into a flowing substance. Its density indicates a composition of iron and rock, similar to Earth. Scientists know its size from the amount of starlight it blocks, and its mass from the gravitational wobble it creates in its star. Combining these measurements reveals its high density, screaming rock and metal. GJ486b completes one full orbit in just under 1.5 Earth days. A year on this planet is shorter than an Earth weekend. It races around its star at blistering speed, locked in a tight embrace that brings it dangerously close to the stellar surface. This proximity is both its curse and its key to discovery. The curse. It's roasted by intense radiation. The key, being so close, makes it easier to study than distant worlds, as it blocks a larger percentage of the star's light during transits, making the signal stronger and clearer. Even stranger, GJ486b is almost certainly tidally locked. One hemisphere perpetually faces the star, baking under constant radiation, the day side. The other faces the void of space, frozen in perpetual darkness, the night side. The border between these extremes, the terminator, is where chaotic phenomena might occur, if an atmosphere exists, attempting to transport heat from day to night. But that's precisely the question everything hinges on: 26 light years. That number sounds vast until you understand its true meaning. In cosmic terms, GJ486b practically lives in our backyard. Our Milky Way galaxy spans 100,000 light years. This world exists in the tiniest sliver of space near our own solar system. The star it orbits, GJ486, is an M-dwarf or red dwarf star, the most common type in the universe, comprising about 70% of all stars. They are small, cool, and dim compared to our Sun. GJ486 has only about 30% of the Sun's mass and shines with less than 2% of its luminosity. You could stare directly at this star from Earth's distance without eye damage, though you'd need a telescope to see its faint red point. Because the star is so dim, a planet needs to orbit extremely close to receive enough warmth for liquid water, placing the habitable zone much nearer to the star than Earth's orbit. GJ486b orbits even closer, explaining its scorching heat. This closeness offers an advantage for scientists. The nearer a planet is, the more starlight filters through its atmosphere during transits, providing a stronger signal and easier detection. GJ486b checks multiple boxes for detectability. It's close enough, large enough, and transits regularly. However, being this close to a red dwarf comes with terrible consequences. These stars, while cooler than the Sun, are far more violent. They unleash devastating flares, massive bursts of X-ray and ultraviolet radiation that blast nearby planets. These flares can increase a star's brightness by 10 to 100 times in minutes. Such an event would strip Earth's atmosphere and boil its oceans. During their first billion years, red dwarfs constantly throw stellar tantrums, bombarding planets with high-energy radiation, tearing away any nascent atmosphere molecule by molecule. Ultraviolet light breaks water into hydrogen and oxygen. Hydrogen escapes, oxygen either escapes or reacts with surface rock, and the atmosphere vanishes. GJ486 is billions of years old now, past its most violent youth, but the damage may already be done. Scientists estimate this star has spent eons bathing its planets in radiation, That's why finding an atmosphere on GJ486b would be so shocking. The planet should be airless, stripped bare, a dead rock circling a dying ember. Yet, the telescope detected water vapor. Somehow, somewhere. Red dwarfs have another trick. They live practically forever. A star like our Sun burns for about 10 billion years. Red dwarfs can burn for 10 trillion years, 1,000 times longer. The universe itself is only about 14 billion years old, meaning no red dwarf has ever died of old age. This longevity creates an intriguing possibility. If rocky planets around red dwarfs can somehow keep or rebuild their atmospheres, they have trillions of years to develop life and civilizations. That's why the question of GJ486b's atmosphere is so crucial. It's not just about one planet, but billions throughout the galaxy. A year on GJ486b lasts only 36 hours. While you sleep through 2 Earth nights, this planet completes an entire journey around its star, tearing through space at roughly 200,000 km. The distance between the planet and its star is only about 2 million miles, roughly 1/50th of the Earth-Sun distance. This breakneck orbit creates bizarre consequences. There are no seasons. A birthday would occur every 36 hours. The concept of a year becomes meaningless. The close orbit also means the star appears massive in the planet's sky. From the day side, the red dwarf would loom about 15 times wider than our Sun appears from Earth, covering a huge portion of the sky as a vast crimson disk. Its light would be dimmer, more orange-red than yellow-white, but its sheer size overwhelming. Scientists calculate this precise orbit by measuring how often the planet transits its star. Every 1.467 days, like clockwork. This mathematical precision confirms the orbit is stable, locked in a gravitational dance for billions of years. However, the planet likely doesn't experience this 36-hour cycle at all. Because it's tidally locked, one side always faces the star, and the other always faces away. Imagine a world where the sun never moves, hanging frozen in one spot in the sky forever. That's the day side of GJ486d. On the opposite hemisphere, total darkness reigns. Between them, the Terminator band experiences eternal twilight. Tidal locking occurs when gravity pulls differently on the near versus far side of a planet orbiting close to its star, acting like a brake on its rotation, until the same side always faces inward. Earth's moon is tidally locked to Earth. GJ486b is almost certainly locked to its star in the same way. The dayside temperature reaches 800 degrees F, but the night side could be hundreds of degrees colder, possibly near absolute zero, depending on whether an atmosphere exists to transport heat. If there's no air, the night side is a frozen wasteland. The Terminator region might be the only place with bearable temperatures. This directly relates to the water vapor mystery. If an atmosphere exists, it changes everything about tidal locking. Atmospheres move, with air flowing from high pressure, cold night side, to low pressure, hot day side. These supersonic winds would transport heat, moderating both extremes. Scientists can test this by measuring the hottest spot on the day side. If it's directly under the star, winds are weak or absent. If it's shifted downwind, an atmosphere is transporting heat. Future observations might reveal the truth, but for now, we only have the ambiguous water vapor signal. 800 degrees Fahrenheit, let that number sink in. Paper ignites at 450 degrees. Lead melts at 669. Zinc melts at 786 degrees. This planet's surface exceeds all these thresholds. If you could stand there, which you absolutely could not, your body would combust instantly. The ground would glow dull red. Any water reaching the surface would flash into steam before forming a puddle. Scientists calculated this temperature by measuring the star's light, how much hits the planet, and how much the planet reflects or absorbs. All numbers point to a world existing at the edge of what rock can withstand. Basalt, common volcanic rock on Earth, softens around 2000 degrees F, so GJ486b isn't quite molten, but different minerals would behave very differently. For comparison, Venus, our solar system's hottest planet, has a surface temperature of about 870 degrees F, remarkably similar to GJ486b. But Venus maintains that heat with a crushing atmosphere of carbon dioxide, 90 times denser than Earth's. The greenhouse effect on Venus is so extreme that its night side stays nearly as hot as its day side. GJ486b, however, might have no atmosphere at all if airless. The day-night temperature swing could be extreme. 800 degrees F on the day side, potentially 300 degrees F on the night side, a difference of over 1,000 degrees. This heat creates a significant problem for the water vapor hypothesis. If water exists in the planet's atmosphere, where did it come from? The planet is too hot for liquid water on the surface, and any primordial water would have boiled away billions of years ago. For water vapor to exist now, it would need a continuous source, the only plausible one being volcanic activity, releasing steam from the planet's interior. Deep below the surface, water could exist as superheated liquid or steam, held by immense pressure, blasted into the atmosphere by eruptions. But this volcanic scenario requires geological activity, a hot interior with convecting rock and erupting volcanoes. Scientists don't yet know if GJ486b is active or dead. For a planet 3 times Earth's mass, staying warm inside for billions of years is plausible due to residual formation heat and radioactive decay, but it's unconfirmed. And this brings us back to the central mystery. Is the water vapor on the planet or the star? Cool spots on a burning star. That's the competing explanation that keeps scientists up at night. Just as our sun develops sunspots, red dwarf stars also develop star spots. But red dwarf star spots are much cooler. While sunspots on our sun drop from about 10,000 degrees F, 5,500 degrees C, to 7,000 degrees F, 3,870 degrees C. Red dwarf star spots can be even more extreme. The star's surface might be 6,000 degrees F, 3,300 degrees C, but a star spot could be 4,000 degrees F, 200 degrees C or less. This temperature difference is crucial because water molecules break apart at high temperatures, but can exist as vapor at lower temperatures. Our sun is too hot for water vapor in sunspots, but cooler red dwarfs can harbor water in their star spots. Scientists have confirmed this spectroscopically. Water vapor exists in the atmospheres of cool stars, pooling in their dark spots. The tricky part: when GJ486b transits, passing in front of its star, it might pass in front of a star spot. The light filtering through the planet's potential atmosphere also carries the signature of the star spot. The two signals mix, making it nearly impossible to separate the planet's atmospheric water vapor from the star spot's water vapor with current techniques. The researchers' computer models, simulating both scenarios, produced transmission spectra that matched the Webb telescope's observations almost equally well. The difference between the models only emerges at shorter wavelengths, below the range observed by Webb's near-infrared spectrograph, NIR spec. This is why additional observations with a different instrument, NIRIS, near-infrared imager and slitless spectrograph, are needed. NIRIS can observe at those shorter wavelengths and could potentially show a divergence. If the water signal strengthens at shorter wavelengths, it's probably from the star. If it weakens or disappears, it's likely from the planet. But those observations haven't been completed yet. The mystery remains unsolved. Red dwarfs like GJ 486 are magnetically active and covered in star spots, sometimes covering 10% or more of their surface. When a planet the size of GJ 486b transits such a star, it's almost guaranteed to pass in front of at least one star spot during the hour-long transit. This contamination is unavoidable. Every transit measurement from a planet around a red dwarf carries this ambiguity. Scientists first recognized this star spot problem in 2018, years before JWST launched, predicting it would be a major challenge. That prediction came true with GJ 486b. Light tells stories. When photons pass through a gas, certain wavelengths are absorbed, creating a unique fingerprint for each molecule. Water absorbs strongly at specific infrared wavelengths. Carbon dioxide and methane have their own signatures. By spreading starlight into a rainbow spectrum and measuring which colors are missing, scientists can read the chemical composition of distant atmospheres. This technique, transmission spectroscopy, is revolutionizing exoplanet science. Here's how it worked for GJ 486b. The planet orbits every 36 hours, and once per orbit, it passes directly in front of the stars seen from Earth. During this hour-long transit, a tiny fraction of starlight passes through the planet's atmosphere, if it has one, before reaching Earth. If air is present, the light interacts with it, and specific wavelengths are absorbed by water molecules vibrating and rotating in response. These absorbed wavelengths are converted to heat, and the remaining light, now missing those colors, continues toward Earth. The Webb telescope collects this light, splits it into a spectrum, and identifies dips where water vapor absorbed light. Scientists observed GJ 486b during 2 separate transits to confirm the signal. The first showed the water absorption feature, and the second showed it again. This consistency meant the signal was real, not noise or an instrument error. Each transit provided enough photons for a detailed spectrum using Webb's NIR-SPEC instrument, which operates at wavelengths between 0.6 and 5.3 microns, the infrared range where water vapor has strong absorption features. The spectrum came back mostly flat, meaning the planet blocked roughly the same amount of light at most wavelengths. A flat spectrum often suggests no strong absorbers or no atmosphere at all. However, at the shortest wavelengths NIR-SPEC could see, around 1 micron, there was a rise, a bump in the data. That bump matched the wavelength where water vapor absorbs light. While not perfect and with large error bars, the signal was there, reproducible across both transits, and consistent with water vapor's spectroscopic fingerprint. This tiny bump in an otherwise boring spectrum ignited an international scientific debate. Flat spectra can have multiple causes. An airless planet produces a flat spectrum. So does an atmosphere with thick clouds that block light equally across all wavelengths. And frustratingly, star spot contamination can also produce a nearly flat spectrum, or complex changes that mimic or hide atmospheric features. Disentangling these effects requires detailed models of both the star and the planet. The researchers compared the observed spectrum to 2 competing models, one with a water-rich planetary atmosphere and another with an airless planet, but water vapor in stellar star spots. Both models fit the data almost equally well. The statistical difference was negligible. This near tie is common in cutting-edge science. At the limit of instrument capabilities, clear answers are rare. Initial observations are often ambiguous, with clarity coming later, through better instruments, more observation time, or new analysis techniques. The fact that scientists observed twice is crucial. Observing once is interesting. Observing twice is science. When the first transit showed the water vapor signal, confirmation was immediately needed. Despite the expense of telescope time, the potential importance justified a second observation. The planet transits frequently, so the next opportunity came quickly. The second transit showed the same water vapor signature. This consistency meant something in that system produces a water vapor signature. The question remained whether that something is the planet or the star. Multiple observations also help average out noise, strengthening the true signal. The two transits occurred months apart. If star spots were causing the signal, they might have rotated to different positions on the star between observations. Red dwarf stars typically rotate once every few weeks. If the water signal came from a specific star spot that rotated out of view, the signal might disappear or change. But it didn't change. This could mean the water is in the planet's atmosphere. Or it could mean the star is so covered in star spots that the planet always passes in front of similar amounts of water vapor, regardless of which spots it traverses. Scientists can't tell which interpretation is correct without additional data. On August 24, 2024, a new scientific paper dropped like a bomb on the GJ486b debate, bluntly titled, "No Thick Atmosphere on the Terrestrial Exoplanet, GJ486b." This paper presented results from two additional JWST observations using a different technique: secondary eclipse spectroscopy. Instead of watching the planet transit in front of the star, these observations measured what happened when the planet passed behind the star. The conclusion challenged everything the earlier transmission spectroscopy suggested. Secondary eclipses reveal different information than transits. When the planet goes behind the star, the system's total brightness drops slightly because we lose the planet's thermal emission. By measuring this brightness drop at different wavelengths, scientists can determine the planet's dayside temperature and look for emission features from its atmosphere. If a thick atmosphere exists, it should transport heat and show spectral features from glowing molecules at infrared wavelengths. The new observations showed neither. The team measured the planet's dayside temperature at 895 F, 463 C, with remarkable precision. More importantly, this temperature was 97% of the maximum expected for an airless bare rock with no heat redistribution. This ratio suggests the planet redistributes heat very poorly, if at all. A thick atmosphere would transport heat from day to night, significantly lowering the dayside temperature below the maximum. But GJ486b's dayside temperature is almost exactly what you'd expect for bare rock. The paper concluded that the planet either has no atmosphere or possibly a very thin one, with less than 1% water vapor or less than 1 part per million carbon dioxide. This result directly contradicts the water vapor detection from transmission spectroscopy. How can both be true? The answer might lie in the technique's different sensitivities. Transmission spectroscopy looks at starlight, filtering through the very top, thinnest layers of a potential atmosphere. Secondary eclipse spectroscopy looks at thermal emission from the entire dayside, sampling deeper layers. It's possible the planet has a very thin, high-altitude layer of water vapor that transmission spectroscopy detected, but not enough atmosphere to significantly affect heat transport. Alternatively, the transmission spectroscopy might have detected stellar water vapor in star spots, not planetary water vapor. The secondary eclipse observations support this interpretation because they show no evidence for atmospheric heat transport. If the planet were wrapped in a water vapor atmosphere, thick enough to produce the transmission spectroscopy signal, that atmosphere should also transport heat. The fact that it apparently doesn't suggests the water vapor isn't there. The August 2024 paper represents the scientific process working as intended. One team reports a detection, another team tests it with a different method, and the results disagree. Now scientists must figure out which result is correct, or whether both are correct, but measure different things. The debate continues. But the new data shifts the odds toward the starspot explanation. Airless doesn't mean a perfect vacuum. Even Mercury, the most obviously airless planet in our solar system, has a wispy exosphere of atoms kicked up from its surface by solar wind impacts. When scientists say GJ 486b might be airless, they mean an atmosphere so thin it barely matters. Pressures millions of times lower than Earth's. You couldn't breathe it or hear through it. For most purposes, it doesn't exist. But it's technically there, detectable by sensitive instruments. Earth's atmospheric pressure at sea level is about 14.7 pounds per square inch. Venus, by contrast, has surface pressure 90 times Earth's, feeling like being 3,000 feet underwater. Mars has about 0.6% of Earth's pressure, thin but enough for weather. These are all thick atmospheres, in that they significantly affect their planets. GJ 486b might have something far thinner. Atmospheric pressure 1/10th of Mars, or 1/100th, or 1/20th. At some point, calling it an atmosphere becomes misleading. It's more like a thin haze of molecules. Such an atmosphere wouldn't transport heat, create weather, or protect the surface from radiation. Yet, it might still produce detectable spectral features if concentrated at high altitudes where transmission spectroscopy looks. The phrase "no thick atmosphere" in the August 2024 paper is carefully chosen. It rules out Earth-like or Venus-like atmospheres, but leaves room for something ultra-thin. The abstract states, the results are consistent with an airless body with a slight non-zero albedo, or a thin atmosphere with less than 1% water vapor. This less than 1% phrasing is crucial. Earth's atmosphere is 0.4% water vapor on average. Less than 1% could still mean significant water vapor by some definitions, just not enough to affect heat transport or produce strong secondary eclipse signals. Understanding these distinctions matters because the definition of atmosphere affects whether GJ 486b counts as a historic discovery or a false alarm. If the planet has even a wisp of genuine atmosphere, it would still be the first rocky exoplanet with confirmed atmospheric gas, a milestone for understanding planetary formation and evolution. But if it's truly airless, and the water vapor signal comes from star spots, then scientists are back to searching for the first rocky exoplanet atmosphere. Red dwarf stars host a cosmic graveyard of dead atmospheres. Billions of rocky planets orbit these cool suns, and most probably started with air. But young red dwarfs unleash radiation storms that strip atmospheres away, layer by layer, until only bare rock remains. This is the M-dwarf planet problem. M-dwarfs are the most common stars, 70% of all stars, and rocky planets around them are even more common. Billions of Earth-sized worlds could orbit in their habitable zones. But if these planets can't keep their atmospheres, they can't support life. Billions of potentially habitable worlds become billions of sterile rocks. Scientists debated this problem for decades. Some argued M-dwarf planets would be universally airless due to intense radiation and close orbits. Others argued planets might hold on through strong magnetic fields, high planetary mass, stronger gravity, or continuous volcanic outgassing. The debate remained theoretical because no one could definitively detect or rule out atmospheres on rocky exoplanets around red dwarfs. GJ 486b was supposed to help settle this debate. It's massive enough for gravity to help retain atmosphere and orbits an older red dwarf past its most violent youth. If any rocky planet around a red dwarf could keep an atmosphere, this seemed a good candidate. The initial water vapor detection sparked hope that atmospheres can survive. But the August 2024 paper, showing no thick atmosphere, revived pessimism. The implications extend beyond habitability. If rocky planets around red dwarfs can't maintain atmospheres, biosignature searches should focus on planets around rarer, harder-to-study sun-like stars, drastically reducing the number of searchable worlds and stretching the timeline for finding life. There's also a mass threshold. GJ 486b, at 3 times Earth's mass, is at the high end for rocky planets. If it struggles, smaller Earth-sized planets have little chance. Conversely, if it does have an atmosphere, it suggests smaller planets might also succeed under the right conditions. The answer dictates which planets are worth studying. Venus and GJ 486b are cosmic twins, separated by vast distances. Both are rocky planets, with surface temperatures around 800 degrees F, 427 degrees C. Both orbit closer to their stars than Earth. But Venus has a crushing carbon dioxide atmosphere, while GJ 486b might have none. Understanding why these similar worlds follow different paths could reveal fundamental truths about planetary evolution. Venus's atmosphere is 90 times Earth's, with crushing surface pressure and sulfuric acid clouds. Its runaway greenhouse effect maintains hellish temperatures. Venus likely started with liquid water oceans, but its closer orbit to the Sun caused evaporation, leading to a positive feedback loop. More water vapor, a greenhouse gas, trapped more heat, evaporating more oceans. Ultraviolet light split water molecules, hydrogen escaped, and oxygen reacted with rocks. Volcanic carbon dioxide accumulated, creating the thick atmosphere. GJ 486b could have followed a similar path. Initial water oceans would have evaporated quickly due to intense stellar heating. But the red dwarf's ultraviolet radiation might have split water apart even faster than the Sun did on Venus. Hydrogen escaped, oxygen escaped, or reacted with rocks, and the water vanished within a few 100 million years. Unlike Venus, GJ 486b might not have had substantial volcanic outgassing of carbon dioxide, or if it did, the stellar wind stripped that gas away, resulting in an airless world. Venus's thick atmosphere provides protection from stellar wind. GJ 486b orbits much closer, where stellar wind is more intense. Even if it tried to build a thick atmosphere through volcanic outgassing, the stellar wind might remove gas faster than volcanism supplies it. Critically, Venus's heat comes from its greenhouse effect, not stellar proximity. Without its thick atmosphere, Venus would be much cooler. GJ 486b's heat is from stellar proximity. Removing any thin atmosphere barely changes its temperature. This tells us GJ 486b's heat comes from external radiation, not internal atmospheric insulation. Venus trapped its own heat. This planet can't. The comparison highlights how small differences lead to wildly different outcomes. Venus got too much atmosphere. GJ 486b got too little or none. Both are hellish, but in different ways. Scientists have found atmospheres on hundreds of exoplanets, gas giants and hot Jupiters, with clear spectral features of water vapor, methane, carbon monoxide, and even atomic metals. These techniques work beautifully for large planets with thick atmospheres. But rocky planets are different. Smaller, thinner atmospheres, if any, harder signals to detect. Until GJ 486b, no one had definitively found atmospheric gas around a rocky exoplanet outside our solar system. A confirmed discovery would shatter a decades-old barrier. It would prove the techniques work, validating years of instrument development and analysis methods. It would show that transmission spectroscopy and other methods can achieve the sensitivity needed for small planets, justifying future powerful telescopes designed for Earth-like worlds. The search for habitable planets would accelerate dramatically, but the flip side matters too. If GJ486b turns out to be airless, it suggests rocky planet atmospheres are even harder to detect than pessimists feared. Current technology might not be quite good enough. Future telescopes would need even better sensitivity, pushing the timeline for characterizing Earth-like planets further into the future. Finding life might become a goal for future generations, not the current one. The historic significance depends entirely on the ambiguous data. If transmission spectroscopy detected real planetary water vapor, and secondary eclipse observations simply missed a thin atmosphere, GJ486b enters the history books. If transmission spectroscopy detected stellar water vapor from star spots, and secondary eclipse observations correctly showed no planetary atmosphere, the search continues. The difference hinges on observations not yet completed. Scientists are careful not to claim victory prematurely. Sarah Moran's statement, "We see a signal, and it's almost certainly due to water. But we can't tell yet if that water is part of the planet's atmosphere," perfectly summarizes the honest uncertainty. Premature claims, later overturned, damage scientific credibility. Better to wait for definitive proof. It's vital to address a common misconception. Finding water vapor does not mean finding life. Water is necessary for life as we know it, but water alone isn't life. Water exists on countless worlds throughout the universe without any biology. Jupiter, Saturn, comets, even the moon have water. Water is necessary, but nowhere near sufficient. Biosignatures are specific combinations of gases produced by life that cannot be easily explained by geology or atmospheric chemistry alone. On Earth, oxygen is a biosignature continuously produced by photosynthetic organisms. Without life, geological processes would remove oxygen from Earth's atmosphere in a few million years. However, even oxygen alone isn't conclusive. Planets can produce it non-biologically, e.g., water vapor split by UV light. The strongest biosignatures are combinations: oxygen plus methane, methane plus nitrous oxide, which are chemically unstable and shouldn't coexist without constant replenishment. A feat life can achieve, but geology struggles with. GJ486b's water vapor, even if confirmed to be planetary, has 0% biosignature value. Water vapor is entirely explainable through volcanic outgassing, requiring no life and providing no evidence for it. It doesn't even suggest the planet could support life, given the 800 degree F, 427 degrees C surface temperature. If life exists there, impossibly unlikely, the water vapor tells us nothing about it. The water is geologically and atmospherically interesting, but biologically irrelevant. Sensationalized media coverage often conflates water findings with imminent alien contact. The reality is far more mundane. Hints of water vapor that might be planetary or stellar. Even if planetary, it might just mean volcanoes are erupting. Setting appropriate expectations prevents public disappointment and maintains trust in science. The story of GJ486b is unfinished. Additional observations with JWST's NIRISS instrument could definitively determine whether the water vapor comes from the planet or the star. These observations are scheduled, likely within the next year or two. If NIRISS shows the water is stellar, the case closes. The planet is likely airless, and the search for the first rocky exoplanet atmosphere continues. If NEARES confirms the water is planetary, even a thin atmosphere counts as historic. Beyond GJ486b, dozens of similar planets await study. Scientists have identified hundreds of rocky exoplanets around red dwarf stars, close enough for detailed atmospheric characterization. Some are even more favorable targets. JWST can only observe a small fraction during its mission, raising difficult choices about prioritization. The Nancy Grace Roman Space Telescope, launching in 2026 or 2027, will join the search. Roman will have different capabilities, including directly imaging some planets, providing complementary data. Ground-based telescopes are also improving. The Extremely Large Telescope, ELT, in Chile, under construction, will have a 39-meter primary mirror, potentially enabling atmospheric studies of rocky planets around nearby stars. The combination of space and ground-based observations will accelerate progress. Longer term, proposals exist for even more ambitious missions, specifically designed to study Earth-like planets and detect biosignatures. Whether these missions get funded depends partly on what current observations reveal. If JWST confirms atmospheres on multiple rocky exoplanets, funding agencies will be more likely to support future missions. The ultimate goal is finding life. Every step toward characterizing rocky exoplanet atmospheres moves closer to that goal. GJ486b might not have life and might not even have an atmosphere, but studying it develops the techniques needed to eventually find habitable worlds. Each observation teaches something. Each ambiguous result points toward better methods for future work. Science progresses incrementally through exactly this kind of painstaking investigation. Within a few years, perhaps sooner, scientists will know definitively whether GJ486b has an atmosphere. They'll know if rocky planets around red dwarfs can survive atmospheric stripping. They'll know where to focus future searches for habitable worlds. The answers will reshape our understanding of how common life might be in the universe. They'll determine whether humanity is likely to find neighbors or whether we're isolated in a galaxy full of sterile rocks. 26 light-years away, a planet either wrapped in steam or bare as the moon orbits its red dwarf star. In laboratories and universities across Earth, scientists wait for telescope time, analyze data, and debate interpretations. The mystery persists, the ambiguity frustrates, but the search continues. Because somewhere in the cosmos, perhaps on a planet much like GJ486b, but farther from its star and cooler, life might exist. Finding it starts with understanding worlds like this one, learning which planets can keep air and which cannot, building the knowledge and tools to eventually answer humanity's oldest question: are we alone? The answer, whatever it is waiting in the light, filtering through distant atmospheres. Join the Stellify science community by subscribing now and hitting the notification bell. Let's unravel the cosmos together.